This conference will now be recorded.
Hello everyone. In last class, we have already started some extraction method of metals from their ores, and some metals we have already covered. Today we will start with zinc. That is how we can extract zinc starting from its ore, which is basically zinc oxide. The most commonly available ore for zinc, that is from which we will extract zinc, is the sulfide salt, that is known as zinc blende. Now, the first method will be concentration of the ore, then it will be isolation of the metal, and finally there will be purification. So these three are the main steps under metallurgy. And the first method, that is concentration, here the method that we will use is froth flotation process. Then by roasting, ZnS, that is sulfide form, will be converted to oxide form by roasting method, because in roasting method sulfide salts are converted to oxide salt in presence of oxygen. This zinc oxide that we have obtained by roasting process, now finally it will be mixed with coke. So this is basically the second step, that is isolation step, where we get the metallic form of the metal, that is the zero oxidation state. So we need some reducing agent because our oxidation state of zinc is +2. So that is why we are using reducing agent coke. It is heated strongly 1673 Kelvin, which is very high temperature. That is, in degree centigrade, is almost 400 degrees centigrade. Okay, and in this, when it will be heated, then ZnO, it will be ultimately reduced to the metallic zinc. And remember, this particular process is known as Belgian process. So this name is only for zinc. And the third method is basically purification. So up to this, that is when you have obtained ZnO, up to this it is concentration, then reduction, which is basically the isolation step, and third step is purification. So now we have already obtained Zn, but it is not pure form. So the remaining impurity we can remove by using some purification method. So the zinc that is formed, it will be immediately vaporizing, and it can be distilled over leaving behind non-volatile impurities. So suppose zinc is containing this type of impurities, which are also metal, cadmium, lead, iron. But how we can remove it? You can remove it by distillation process. So distillation is one of the purification process, and zinc can be used in this process. But we know that all the methods we just cannot use arbitrarily. There must be some logic behind that. Now distillation is possible here because Zn has melting point which is low compared to its impurities. So that is why impurities will be remaining behind. So that is it is written, only Zn will be vaporized and it will condense and distill over, leaving behind the non-volatile impurities. That means impurities are having higher melting point. So that is why they will not be converted to vapor. Now this gas which is containing Zn vapor, it will be collected, and after condensation it will be ultimately converted to solid zinc. That is, first it will be zinc vapor, then it will be liquid, and ultimately it will be converted to solid zinc. And pure zinc obtained by this method is known as spelter zinc. It can further purified by fractional distillation. That is, after doing the first distillation, then again it can be we can do further purification, but depending on what type of pure form we require. Suppose if we require 100% pure Zn, so obviously we have to do rigorous purification method. But suppose if 98% is okay, then we don't have to do purification in rigorous way. So it depends on what is the amount of percentage of purity that we want. Now if we do this fractional distillation further, then the zinc finally that we are getting, this is very having high purity. Okay, and another method by which we can get pure zinc is electrolysis method. So one is distillation, which is mostly done. Another way is electrolysis, which is another process of purification. Remember, under purification we have discussed total 8 methods, And electrolysis and distillation, these two are two of these 8 methods. Now when it is electrolysis, then as cathode, the electrode that we use is pure zinc, and the impure zinc, that is the zinc that we have obtained in this process after reduction with coke, that impure zinc we have to use as anode. And this is not just for zinc. This method we use for all the other metals except aluminium. In case of aluminium, we do not use pure aluminium as cathode or impure aluminium as anode. In that case, carbon is basically used, that is graphite. But except aluminium, you will see most of the cases always the pure metal will be used as cathode and the impure metal that will be used as anode. Okay. And for electrolyte, because we are doing electrolysis, obviously electrolyte is required. What is the electrolyte? Electrolyte is mixture of ZnSO4 in presence of dilute H2SO. When we are passing current, impure zinc gradually will dissolve. That means zinc will lose electron and it will be converted to Zn2 plus. An equivalent amount of pure zinc is deposited at cathode, because at cathode there is reduction. So the zinc 2 plus that we will be getting from anode, that is impure anode, now this zinc 2 plus, it will be reduced to metallic zinc. So ultimately what will happen, gradually the pure zinc rod that we have used as cathode, the size will increase because more and more zinc will be deposited on its surface. And also in the left hand side anode that we are using, it will be gradually corroded. Okay, so this is the method of extraction of zinc from zinc oxide. Is there any doubt? Regarding extraction, here we will have one problem. We have to find out incorrect statement. It is single choice, that means 3 statements will be correct and 1 statement will be wrong. The first statement, in the extraction metallurgy of copper, silica removes Fe2O3 which is present in the matte by forming FeSiO3. Now, extraction metallurgy of copper, the copper that we obtain, that is actually known as copper matte. That is here mentioned as only by the term matte, but it is actually copper matte. Okay, and it is saying that silica is used to remove Fe2O3. Now it is extraction metallurgy of copper, that means you are basically extracting copper. So Fe2O3, it must be the impurity, that is the undesired part. And when we want to remove impurity, that is also known as gangue, we use flux, because flux, F for flux, it combines with gangue, G for gangue, and it produces slag. Okay, so in this way removal of gangue becomes easier. Now when gangue is acidic in nature, the flux must be basic in nature and vice versa. Here Fe2O3 is metallic oxide, that means it is basic in nature. So the flux that we have to add, that must be acidic in nature. And silica is acidic. So that is why here this statement is basically correct, and SiO2 when react with Fe2O3, ultimately it will form FeSiO3. So this statement is true. Next statement, cast iron has lower carbon content than pig iron. When we have discussed extraction of iron from its oxide, then we have seen first we obtain pig iron. After that, from pig we get cast, and finally we get wrought iron. I have written W for wrought. Okay. Now pig iron, it is containing most of the impurities, and carbon here is present as impurity. And gradually, as we are moving from pig to cast to wrought, carbon content is becoming less and less. That means cast iron will have lower carbon content than pig iron. Basically in pig it is 4% carbon, in cast it is 3% carbon. So this statement is also correct. Next statement, out of carbon and carbon monoxide, that is C and CO. CO is a better reducing agent than carbon for Zn. So here you are trying to reduce ZnO to Zn. Here it is having oxidation state +2. Here it is 0. So this is reduction. But for this reduction method, you will use copper or CO. That is the question. Here it is mentioned that CO is better reducing agent. But is this true? And answer you can get only by considering the Ellingham diagram. Okay, but we will come to that point. But before that, just we will see the last statement, that is cryolite, which is NaLO3. Okay, this is used in the extractive metallurgy of aluminium. This is obviously correct, but here the reason that is mentioned only to lower the melting point of the mixture. Okay, so cryolite is basically used to lower the melting point of the mixture. That is actually true. So among C and D, if D is true, then C must be wrong. But why C is wrong, that we have to see. So here we have the Ellingham diagram. In this Ellingham diagram, first we will choose that line which is basically necessary for us, because here we have several lines, all the lines are not required. So for zinc system, here this is the line. Okay, and for carbon, that is carbon is converted to CO or CO2, that line is, you can get C2CO and CO2. So one is this one, C is converted to CO, another one is C is converted to CO2. And the line for carbon monoxide, where carbon monoxide is converted to CO2, that one is this one. Now compare. We know that when we are considering any two reaction, which system can act as reducing agent, you can very easily understand whether this line is present below it. Now see the line for CO2, this is above the line of Zn. So CO cannot be used as reducing agent. Okay. Here zinc can used as reducing to reduce CO2 to CO. But the reverse reaction is not possible because the line of CO2 that is above the line of zinc to Zn. Okay, so CO cannot be better reducing agent. So it means the statement C is wrong. Now out of carbon and carbon monoxide, if CO is not better reducing agent, then carbon should be the better reducing agent. But why it is so? Now see the line for carbon after these two temperature, here it is below the line of Zn, and if you consider the other line, when carbon is converted to carbon dioxide, after this temperature, that is around here temperature, and this one is around 800, above this temperature, now the line of C2CO2, that is below the line of Zn. So basically the line of carbon is below Zn, whether it is converted to CO or CO2. In both cases it is below Zn, particularly after these two temperatures. So it means that carbon can reduce ZnO to zinc. Okay, so this statement is basically false, and we have to find incorrect statement. So this will be the correct statement. Any doubt? Should I repeat once more? Next is extraction of silver from silver ore. Here the method from which we are starting the process is known as MacArthur forest cyanide process. Sometimes it is simply also mentioned as cyanide process, but this is a full name. This is a metallurgical technique for extracting gold and silver. So both gold and silver can be extracted by this method, but here we will focus only on silver. But remember, for gold also similar techniques will be used. Silver from low-grade ore by converting them to a water-soluble coordination complex. So both for gold and silver, what we do, we take the low-grade ore of gold or silver and we convert them to water-soluble coordination complex. So this is the overall statement, that is what is actually happening in this process, that is mentioned here. But now we will see step by step what is happening. The low-grade ore that we have taken is argentite, that is the sulfide ore of silver. This is a very cheap source, that is low-grade ore. Now First it is crushed, fine, and concentration of ore is done by froth flotation process. So froth flotation process is the one of the method of concentration which is done in the first step. Now after this process, froth flotation, next what we do, okay, before going to the second point, here we have the picture for froth flotation process. In this, what we are doing, we have taken the ore, and after this froth formation, that is froth bubbles carrying sulfide ore particles. So here see the sulfide ore particles that are actually above, okay, in the form of froth, and this froth is generated by using bubbling compressed air, and in the lower part there is water which is containing the pine oil, and in this portion basically the impurities will be remaining, and see the gangue is deposited here. So after this process, next step is this concentrated ore that we have obtained from froth flotation process. It is treated with very dilute aqueous solution of sodium cyanide. See, it is very dilute, 0.4% to 0.7. So it is treated with this aqueous solution of NaCN, and NaCN is water soluble because it is sodium salt, and current of air is also passed. Now here basically this coordination complex is produced. So here Cn is acting as ligand, which is that is 2 cyanoligand surrounding silver, and silver is having oxidation state +1. So +1 and 2 negative charge coming from cyano, overall charge is -1, and that is balanced by sodium plus iron. So this type of coordination complex, which is basically water soluble because it is sodium salt. Okay. Now this water soluble coordination complex, what will be the next method? This solution is filtered, and the filtrate containing the complex will be used to recover silver. So obviously this part will be in filtrate part because it is soluble. Okay. Now this filtrate part containing the complex, that will be treated with zinc dust. So why we are using zinc dust? Zinc dust is basically used for reduction purpose. Here Zn is having 0 oxidation state, silver is having +1 oxidation state. But if these two metals are exchanging their position, now Zn will come here, silver will be converted to silver 0. So ultimately you are getting reduced silver, and zinc cyanide complex is produced. So here zinc is basically more reactive metal compared to silver. So that is the reason zinc can reduce silver. And then in the last step of electrolytic refine, up to this process it is isolation. This process up to this, that is froth flotation and coordination complex formation, it is the first step, which is concentration of the ore. Second step is isolation, where we mainly do the reduction. And final step is purification. And we know there are different methods for purification, but which method we are using? We are using electrolytic purification. Here the impure silver is made the anode. That means that in place of anode you will take impure silver, and a thin sheet of pure silver will be taken as cathode. Remember, in case of zinc also we have done the same thing. So this is common, except aluminium. In all the cases, always the pure metal is taken as cathode and impure metal is taken as anode. Electricity is passed through the solution of silver nitrate. This is the electrolyte, and silver gradually will be deposited at the cathode. So the size of cathode, that is the thin sheet of pure silver, that will be increasing in size gradually, and anode will be corroded. That is impure silver in place of anode, that will be gradually corroded. Okay, so any doubt how we can extract silver from silver ore? All the three steps are clear. This is the first step, then isolation, and finally purification. Should I repeat? So the process that you have seen in the previous slide, if we present it in the form of flowchart so that you can remember it easily, it will be like this. First, argentite, that is Ag2S, silver sulfide. It is concentrated by froth flotation, where the powdered ore mixed with water, pine oil and air, and froth is formed. Now the froth is basically carrying the sulfide particles. Then cyanidation, that means, remember, we are treating this concentrated ore with sodium cyanide solution, which is very dilute in presence of air, and there is formation of this type of complex. Now this complex, it will be treated after filtration, it will be reduced. Here it is also mentioned how the side product is removed. Side product is treated with oxygen and water, because we have also added air. Now air is basically the source of oxygen. Okay, so Na2S, which is the side product that is treated with oxygen, it is converted to sodium sulfate. So when it will be filtered, it will remain in the residue, and in the filtered portion there will be mainly this soluble, water soluble complex. After filtration there will be reduction. So this is the reduction method. Zinc is reducing and itself is converted to Zn2 plus. Okay, so we are getting black PPT of silver. Now this black PPT, it can further fused with KNO3, though this step is extra, it is not mentioned in the previous slide, but it can also be done. Fused, and we are getting some compact mass. Now this compact mass of silver, finally we are doing the purification method, where anode will be the impure silver that you want to purify, and cathode will be thin sheet of silver. Electrolyte is AgNO3 in presence of acid. Pure silver will be treated as cathode. So gradually cathode will be increased in size and anode will be decreased in size, and in the cathode you will get pure silver in the deposited form. Okay, so this is a flowchart for extraction of silver. After filtration, this is the next method. So all the extraction process of metals from their ores we have discussed, total 5 to 6 metals. Now we will see what are the applications of metals, though it is mostly to remember. There is nothing much to discuss, but still I am trying to mention if there is anything important. In the construction industry, there is use of metals. So there are actually different fields where you will see the application of metals. Construction industry, very important field, and mainly metals like iron, steel, among others, are the main materials that are used for construction of building, etc. Okay, cast iron, which we get from pig iron, that is the most important form of iron, which is used for casting stove, railway sleepers, pipe toys, etc. It is also used in the manufacture of wrought iron and steel. So remember, wrought iron we get from cast iron. Wrought iron, it has some specific applications. So cast iron and wrought iron, these two are mainly used, not pig iron, because pig iron is that iron which you get first after the extraction. Then further it is converted to cast and wrought. Another field is decorative product. Now when we are talking about decoration, it is obviously the costly metals that will be used here. Here you will not see the use of iron, steel like that. So here we are using these costly metals, platinum, gold, silver, because they are the precious metals, high economical value. For making jewelry, decorative pieces also, these are used. Electronics. Now when electronics we will use some metals, it must be good conductor. Okay, now though conductivity, it is the common property of metals, but some metals are there which are very good for this purpose. Metals are good conductors of electricity. They are used to making wires and parts for equipment and gadget that will be used in electrical current related things. Now copper is a very good metal for this purpose. It is used for making wires, which is used in electrical industry. This is the third field. Next field we will see it is machinery, refractory, automobiles. Okay, here obviously iron is used, but some other metals like aluminium is used. And then if we consider utensils that we used at kitchen, that are mostly made of steel and aluminium, and sometimes copper is also used. Now some other applications, that is miscellaneous applications, if we consider, they play important role in security for making locks, doors, etc. And apart from this, sometimes furnitures are also made from metal. Okay, for example, from wrought iron, bed, furniture, all these are made. Table. They have used in military where they are using for manufacturing weapons and ammunition. Ammunition is basically bullets. Okay, some metals are used in galvanizing to protect metal from rusting. So iron, which is very prone to rusting, if we galvanize it with zinc, that we have already seen in detail, that is what is the principle behind this process in electrochemistry chapter. So for galvanizing purpose also, metals coating of metal is done so that rusting can be avoided. Next, alloy and their importance. Now what is alloy, that we have to know. If you take pure metal, that is there is no impurity, then what happens, it is also prone to corrosion, and very good example is rusting. So because of presence of moisture and gases in atmosphere, these metals tend to erode, or you can say there will be oxidation. So for example, if you take iron, if you keep it open air in presence of moisture and oxygen, especially that is H2 and water and oxygen gas, it is there will be rusting. Though rusting is very slow process, but still because of rusting there will be some corrosion. But if you make alloy, now alloy is basically how it is made. Some other metals are also used, or sometimes non-metals are also used. So metals in alloy form are now resistant to corrosion. So when you are making alloy by taking some other metal, so it is basically metal in metal. You can also say it is solid solution. Why solid solution? Because here solvent, solute, both are actually solid. So it may be mixture of two metal. Suppose one is N, another one is N prime. It may be metal plus some non-metal. That is, if you mix carbon with iron, you will get steel. So that is also alloy. So either two metal, different metal, or it may be more than two, or it is mixture of one metal and non-metal. Okay, both are possible. But why we are doing so? Because here the purpose is to make it more resistant to corrosion. So now if you see compare pure iron and steel, obviously you will not get rusting from steel very easily. So it is more longevity is increased. So it is when you are making alloy, it is having now more strength and last for long time compared to pure metals. So this is the purpose of making alloys. And now we will see some examples of alloys and their application. In right hand side column, we have the name of the alloy. In the next column, we have composition, that is what is the percentage of metals or if there is any non-metal, and their application. Now there are different types of steel actually, but when we say it is stainless steel, it is basically mostly it is iron. Obviously iron will be the main part, but there is also mixture of some chromium or nickel, that is the other metals we are using, and these are the applications. Next, coin metal. In coin metal, as you can see from the name, you will be getting the idea of what may be its purpose of using. It is basically used in making coins. So here 3/4 part is actually copper, and 1/4 part is nickel. Then duralumin, here 95% aluminium, but we also have 4% copper and very low percentage of manganese. It is mainly used for construction of aeroplane, ship, etc. Next is solder metal. It is 1:1 composition, 50% tin, 50% lead. Electrical one. Del Elni. Now this is, see, from the name you can easily understand, because it is aluminium, it is nickel, and you can consider it as cobalt. Okay, so if you look at the composition, you will see that there is some range. In the previous examples here particular values are mentioned, though in some other that is different books you will find different figures. Suppose in some cases it may be mentioned that 96 or 94, but more or less it is around 95. And for alnico, these are the range in which this metal can remain. Now see here how many metals we have: aluminium, nickel, cobalt, copper, titanium, total 5 metals. It is a ferromagnetic substance used in permanent magnets. Then gunmetal, which is also known as red brass. Now these names, actually sometimes you will get question where the name will be given and it will be asked that which metals that are present. So it is not always necessary to remember the exact percentage, and that is also very difficult, but just try to remember what are the components that are present. Fine. So in gunmetal mainly it is copper, but we also have presence of tin and zinc. Brass. So in brass it is almost 3/4 part is copper, and sorry, not 3/4 part, 2/3 part, and this is 1/3 part, which is zinc. Then bronze, which is mainly made of copper, but tin and 5% of Mn aluminium, all these are also present. Then sterling silver, from the name you can understand it is mainly silver, but it is not always necessary. If silver is mentioned, silver has to be present. That is not important, because see, German silver, here also mention of silver, but in this you do not have any silver. Okay, only in sterling silver it is matching, and very low amount of copper. Then bell metal, copper and tin. Nichrome. So nichrome, from the name we can understand it is nickel and chromium must be present, but here we also have iron and manganese. And German silver, it is containing copper, nickel, zinc, but there is no presence of silver, but still it is called German silver. Okay. The incorrect statement is, among 4 statements, one of them will be wrong. Bronze is alloy of copper and tin. What we have seen? See, in the second row, bronze is made of copper, tin, Mn and aluminium. Sometimes it is not always necessary that the low percentage metal that is present, in this case manganese and aluminium, even if that is not mentioned it is fine, but the main 2 components must be present, that is copper and tin. But it is not copper and sorry, it is copper and tin mentioned, that means it is correct. So this is not the correct option, because we have to choose wrong state. Next statement is, it is true, cast iron is used to manufacture wrought iron. Now cast iron, it is made from pig, and wrought iron, that is made from cast. That means this statement is also correct. Then German silver is an alloy of zinc, copper, nickel. Now this is also true, because German silver, it doesn't contain any silver. Fine. So obviously the last statement will be false. Brass is alloy of copper and nickel, but actually brass is alloy of copper and zinc, not nickel. See, the first row, it is mentioned 34% zinc, 66% copper, that is brass. So there is no nickel. So the last statement is not correct. So option 4, that will be the correct option. Any doubt?
No, ma'am.
Major component in gunmetal. Now just have a look in the previous tables. Gunmetal, in the last row, red brass, it has another name, copper, tin and Zn. Now copper, tin and Zn, that is mentioned in option 2 only. Okay, in the first one we have only copper and sorry, Zn is also not there, only copper is there, but these are metals are not present. Then copper, zinc, nickel. These two are fine, but nickel is not present. And here copper, nickel, nickel and iron not present, only copper is present. So this is the correct option, that is option 2. So these are actually completely memory based question. There is nothing to discuss much. Now this problem is related to Ellingham diagram, and here we have to find the correct statement among these four. Okay. The first statement is saying that at 1400 degrees centigrade, aluminium can be used for extraction of zinc from Zn. So the meaning of this statement is that you can convert ZnO by using aluminium as reducing agent, and you will get Zn and the oxide of aluminium. So this reaction is possible only when the corresponding del G value is negative. Now del G value will be negative if the line for Zn to ZnO, that will be above the line of aluminium to aluminium oxide. Now if we look at the lines, and remember temperature mentioned 1400. 1400, it will be somewhere between 800 and 2000. Suppose it is here. Now if you draw a line, this is the line for zinc and this is the line for aluminium. Now aluminium at this temperature, it is far below Zn, and when it is below, that means this reaction is possible. Here aluminium can be converted to Al2O3, and the reverse reaction of this one is possible. So that means the first statement is actually the correct statement, that is option 1 is the correct statement. But we also have to see the other statement why it is not correct. At 500 degrees centigrade, that means just follow this dotted line. It is saying that coke, that is carbon, can be used for the extraction of zinc from Zn. That means this reaction must be possible. Plus CO or CO2. Now for this, we have to first see the line for Zn to ZnO at 500 degrees centigrade. This is the line. And the line for carbon to carbon monoxide, this is the line. Now see, Zn line is below the line of carbon. So here Zn, that is carbon, cannot act as reducing agent. Okay. So this statement is false. Coke cannot be used for the extraction of copper from Cu2. This is the line. Here no temperature is mentioned. This is the line for copper. This is the line for carbon. Now just from the beginning, the line of carbon to CO, that is much lower than the line for Cu to Cu2O. So obviously coke can be used, but here it is mentioned cannot be used. So this is not correct. Last statement, 800 degrees centigrade. That is this temperature. Copper can be used for the extraction of zinc. That means it is saying you can use copper as reducing agent for the reduction of ZnO to Zn and Cu to Cu2O. Now is this reaction possible? See here at 800 degrees centigrade, the line for copper is this and the line for Zn is here at this temperature. So here the line is much below than copper. That means Zn can be used as reducing agent. That is here this reaction is not possible, but reverse reaction is possible. Reverse reaction means starting from Zn and Cu2O, Zn can reduce Cu2O from +1 state to 0 oxidation state and itself will be oxidized to Zn. So reverse reaction is possible. That means this statement is not correct. Here correct option is option 1. So should I discuss the problem once more? Is it fine? All the statements clear? Next question, here we have to match the column. In column 1, we have different refining methods. Refining methods means different purification method. Remember, 8 methods are total there that we have discussed. In column 2, the corresponding method. So basically, you have to match that which purification method you will use for these 4 methods. Liquefaction, it is basically used for which method? Okay. Now see, this, if you find that you cannot remember, just go for the next one. The next one is zone refining. Remember, in zone refining we use this type of metal rod, and there is a circular heater like this, and gradually when the heater is present, there will be that is difference of melting point is there, that is the impurity that is present in the metal rod, that will have different melting point. Now impurity having higher melting point, so when the coil is here, there will be only the metal in liquid form. So gradually it will be in melted condition and it will be transferred towards right hand side. So this method is discussed in detail with picture, and we have seen this method is mainly used for group 13 or 14 metals, okay, that is gallium. Now even suppose for these also, if you have any doubt, just go for the next one. Now Mond and Van der Waals, both these processes are basically under vapor phase refining method. Under vapor phase there are actually two methods we have discussed, okay. Now when it is Mond process, it is specially for nickel. When it is Van der Waals, it is for Zr and titanium. Now Mond is B. It is very important. That is this process, Mond process related question you will see, it is very frequent, Mond process and also Van der Waals. So try to remember these two. So Mond process, it is related to 3B, that means 3 is associated with B. Now 3 associated with B, that you can find in option 1, in option 3. So these two we can cancel. And Van der Waals is related to Zr, that means 4 is associated with A. Now 4 associated with A, that we can find here. That means this should be the correct option. So just based on these two, you can decide which option will be correct. Now if it is correct, one is related to C, that means liquefaction is related to Sn. In liquefaction process, what we do, we take this type of slopy arrangement where the metal is basically having lower melting point. So when heat is given, the metal will be gradually in liquid form and it will be stored here, and impurities that will be remaining on this surface, okay. So this is liquefaction method, and tin is mainly used in liquefaction method. So one is related to C and zone refining. Remember, this is zone refining, which is mainly used for group 13 and 14 metal. So gallium is group 13, so that is why it is used in zone refining. So here correct option is option 3. 1 C, 2 is D, that is only the remaining, 3 is B, 4 is A. Okay, any doubt?
No, ma'am.
Arrangement 1 to 4, sorry, among statement 1 to 4, the correct ones are, that means more than one statement may be correct, okay. Now if we look at the option, in first option all the statements are correct, second option only 3 statements correct, third option here also only 3, but it is B, C, D, and in option 4 only C and D correct, okay. Limestone is decomposed to CaO during the extraction of iron from its oxide. Now from iron extraction we use blast furnace. Remember this type of instrument we have used where different temperatures are there. As we move down, there is very high temperature around 2000 degrees centigrade, and then around, that is the first temperature zone, that is lowest, which is 800 degrees centigrade, and here we have intermediate temperature. So in this case what we use limestone, which is basically calcium carbonate, and it is mixed with the ore. Now why we use this compound? Because it is heated. When it is heated, it is decomposed to calcium oxide and CO2, and this calcium oxide is actually used as flux, because here the impurity that is present is silica, and calcium oxide reacts with the impurity which is gangue, and it produces the slag, which is calcium silicate. So this statement is basically correct. Next statement, in the extraction of silver, silver is extracted as an anionic complex. Remember, in extraction of silver, we have seen this type of complex formation, right? Now, this is complex, but complex may be of different type. It may be anionic, it may be cation. Now, sorry, it is one name. If you remove this sodium, there is negative charge. That means it is an anionic complex. So this is also true. Next statement, nickel is purified by Mond's process. Now this we have just seen in the previous problem. So this is also correct. Zr and titanium are purified by Van Arkel method. This is also correct. So all the statements are correct. That means correct option will be the first option. So here we have some, that is the answer is written here. For the first statement, it is limestone which is decomposed to this, and CaO, it reacts with silica and it forms the slag which is calcium silicate. Second statement is true because it forms this type of complex. This negative charge is balanced by sodium ion. C method, nickel is purified by Mond's process. Now Mond's process, Van Arkel process, both are under vapor phase refining, where we first make some volatile complex of the metal, and this volatile complex further it is decomposed and we get finally pure nickel. The same method is also used for Zr, zirconium, for titanium, but here we use not carbon monoxide, we use iodine. That is Zr iodide and titanium iodide is produced. So all the statements are correct and option 1 is the correct option. Any doubt? Any doubt?
No, ma'am.
Aluminium is extracted by electrolysis of bauxite. Now bauxite is the ore of aluminium, where the main component is alumina. Okay, and some other impurities are also there. Alumina is simply Al2O3. Alumina mixed with molten cryolite, NaLF3. Okay, NaLF3, it is basically that is cryolite. Why it is used? There is a particular reason for that. And the last option, it is simply cryolite. But which option is actually correct? Here correct option is alumina mixed with molten cryolite. So when you will do the electrolysis, obviously we have to take salt of aluminium. But why we are adding molten cryolite? The reason behind it is that alumina is mixed with cryolite, which is also containing aluminium. That is, aluminium is also present in cryolite. But remember, here the reason for addition of cryolite to alumina is to decrease the melting point. And this is very important factor related to this fact. There is frequent question I have seen. So it decreases the melting point. This is the first reason we are adding it, and it also increases the conductivity of the ions. So both these are necessary. That is why this is added, and option 3 will be the correct option. Next question, heating mixture of Cu2O and Cu2S, it will give which of these? Now try to remember when we have discussed isolation method, that is you are getting metallic form, that is a zero oxidation state of metal starting from its salt form, that is the oxidized form. There are different methods we use. Sometimes we use carbon for reduction. Sometimes we use some more electropositive metals for reduction. And another method is also there, which is known as self-reduction. So here we do not add any external reducing agent. The compound itself acts as self-reducing agent. That is why we call it self-reduction method. So here what we do, Cu2S is converted to Cu2O first, but all the sulfide is not converted. Some of Cu2S first converted to Cu2O. So now in the medium you have both Cu2O and Cu2S. So when these two are reacting with each other, there is basically formation of Cu, and that is metallic copper, and also there is formation of sulfur dioxide. Okay. So see, this is a cell reduction. It is occurring when you are heating these two together. Here copper is removed in the form of Cu0, and S and oxygen together is making sulfur dioxide, which is gas. So here we are not using any external reducing agent. They are itself reacting with each other, and they are converted to metallic copper. So correct option is copper plus SO2, that is option 1. During the process of electrolytic refining of copper, that is purification method, by electrolysis, some metals present as impurity settle as anode mud. These are which of these mixture? Remember, in anode, when we do electrolytic refining, in anode we always take impure metal. That means here it is impure copper that you will take in anode. There will be different types of impurity, but some impurity, it will be present as metal ion. That will be, as it is ion, it will be obviously in the electrolyte. But there are some metals which are not in ion form, that is, they will remain as zero form. So when metal is in zero form, they cannot be in solution phase. They will be in solid state and they will be deposited just below the anode. Okay, so that is why it is called anode mud. Remember this picture that we have already discussed. Here I have given this picture again, and impure copper as anode, pure copper as cathode, and here the impurities, different types of impurities are there. Copper is the important metal that you are extracting. So just see the other metal ions that are present. These are present in M2 plus form. So M2 plus will always remain in the electrolyte, that is in the solution phase. But there are some metals which are noble metal basically. They are very highly unreactive. They will remain in zero state. And see, all these are very costly metals, right? They will be deposited just below the anode because they cannot go into the solution phase. They are in zero state. So that is why they will be deposited here. Now look at the options. Tin,
Third
silver.
option.
Yes. Which option? Which option is correct?
Third, ma'am.
Yes, this one. Because other options, both these together are not present. It is partially correct, but not fully correct. Now this anode mud is very important because see, these metals are actually very costly metals. Okay. The blister copper used as anode. Blister copper basically, as this is a refining method, so this is the last method. Before this method, you have already done the isolation and concentration. So after isolation, the copper that we get, that is known as blister copper because of some blister type of appearance on its surface. So this blister copper, which is used as anode, in the impurity, the more electropositive metals like Fe, Ni, Zn, all these are basically impurity. They will be soluble because they will remain in the ionic form, Zn2 plus, Fe2 plus, Ni2 plus. But the less electropositive metals, that is the inert metals that are not taking part in reaction very easily, they will be remaining in the zero state, and they will be mixed with other impurities and they will settle down as mud. It is also called sludge at the bottom of the anode. And this is called anode mud, and this is very important because from this anode mud you can again recover all these metals because they are very precious. So that is why anode mud is very important. So here correct option is option 3. This will be the last question. Which of the following factors is of no significance for roasting sulfide ores to the oxide and not subjecting the sulfide ores to carbon reduction directly? So sometimes we have seen when we have any metal sulfide, suppose we have M2S metal sulfide, it may be copper. Okay. Now this sulfide, first it is converted to oxide, and then this oxide is treated with carbon, that is a reduction. You get metallic form and carbon is converted to carbon monoxide. But directly we do not do, that is we do not do the reduction directly on M2S. That is this type of reaction we have not seen. Okay. sorry, it is capital S, carbon disulfide. So why we do not do this reaction, but we actually do the second one? Okay, that is mentioned here. Now this is established fact, but we have to find out which statement is of no significance related to this process. That means there are total 4 statements. Which of this statement is not important, or it may be also that which of this statement is actually not correct. Fine. Now here the first statement is saying metal sulfide are thermodynamically more stable than CH2. Now see, this is actually correct. Why? Because M2S, if it is more stable, then the forward reaction is not possible. Then the backward reaction will take place, because always the system will try to move towards more stable compound. So that is why here this method is not possible, because whenever you will try to reduce M2S with carbon, you will end up with M2S, because this reaction will not take place, because a metal sulfide is more stable. So this statement is important and it has some logic behind it. Next is CO2 is thermodynamically more stable than CH2. Now when you are actually here, CO may be the other oxide of carbon, it may be CO2 also. So CO2 is the byproduct when you are doing the reduction over oxide. CH2 is the byproduct when you are doing the reduction over sulfide. Now obviously CO2 will be more stable than CH2. That is why here the forward reaction is possible. Backward reaction, it will not be so much important. So CO2, if only it is thermodynamically more stable, then only this observation is possible. So this is also significant, important. Next is metal sulfides are less stable than the corresponding oxide. Now metal sulfides, if they are less stable than the corresponding oxide, that means M2S is less stable than M2O, then what it means? It means it is less stable, that means it will not try to take part in reaction very easily, because it is less stable. That means M2S is more reactive than oxides. But if M2S is more reactive than oxide, you will be having this reaction very easily. But actually that is not happening here. Metal sulfides are actually more stable. That is why you are converting M2S first to M2O, because it is more reactive. And as it is more reactive, this reduction will be now facile method. Okay. So this statement, that is metal sulfide are less stable than the corresponding oxide, this is of not having any significance, and this is actually the correct answer. And the last statement, it is very easy to answer, because we know CO2 is gaseous in nature, it is gas, but CH2, it is actually volatile liquid. So under normal conditions, CH2 is liquid, CO2 is already in gaseous form, so obviously CO2 will be more volatile. So this statement is also correct. And when the byproduct is gaseous in nature, its removal will also be very easy. So this is also important for this observation. Now all the points we have in this table. The first point, that is reduction of metal sulfide by carbon reduction process. It is not spontaneous, that is this reaction is not spontaneous, because free energy del G for such process is positive. So it is not spontaneous. Second statement, reduction of metal oxide by carbon reduction, it is spontaneous, that is this method is spontaneous. Why? Because del G is negative. Then CO2 is more stable than CO2. Okay, here it is related to second statement. So this is also correct, and metal sulfides are more stable, but here it is mentioned it is less stable. So this is actually you can say it is, because it is in the question it is asking which is of no significance. It can also be asked in another way, that which of this statement is actually not correct. So metal sulfides are basically more stable, so this is the correct option from both point of view, whether it is false statement or insignificant statement. Okay, so option 3 is the correct option. Is there any doubt?
No, ma'am.
And regarding the other slides, for the overall, any doubt you have? So we will end the session here, as there is no doubt. Thank you for listening.
No doubt, ma'am.